what is easy, but you cannot apply if you don't know how to analyze. Okay, so analysis is the key for this topic. So there are things I want to highlight over here. Okay, so this is rule number 1. Okay, so I'm going to put rule number 1. So I'll highlight to you. So there are 4 rules. Okay, you don't remember all these 4 rules. Okay, we are done. Okay, so rule number 1. Okay, rule number 1. So rule number 1 that I'm gonna state now if I can find the rules on my notes. Okay, so rule number 1 is V and I. So the shear force and the second moment of area are constant regardless okay on the point of analysis. Okay, so this is critical. Okay, so rule number 1. Okay, so what do I mean by that? Okay, so there are 2 formulas, as I said, that we're going to apply. Okay, there are 2 formulas that we, so it's going to be Q is equal to VQ over I, and the other one is shear is equal to VQ over IT. Okay, so whatever we do from here on, right, these 2 values are constant depending on the structure. Right, depending on the question and on the structure, V and Q are always what? Constant. Q over here is the variable. Variable means it can change. And Q and T over here are the variable, depending on the point of interest. So what do I mean by that? What do I mean by this term? So let's say, for example, now we have a cross-sectional area. So we have a cross. So I'm going to draw a cross-sectional area. What do I mean by cross-sectional area? So if I were to draw a transformation, this is X and this is Y. Okay, that's X and that's Y. So we have, for example, for this case, I'm going to draw a simply supported beam. Okay, we're going to have a simply supported beam. So point A, point B, and this is where our P is applied, right? So now we're going to view it from the cross-sectional view. So we're going to view it from cross-sectional view. So this is our Y and this is our Z. So I do apologize. So this is our rotation in the Z, right? So from here, this is the rotation on our X, right? So this is our cross-sectional view. AA. Okay, so let me highlight where it's AA. So I draw a line down here. This is my line AA. Not good to call it AA. Eugene, what's wrong with you today? We have point A. This is our line CC. Okay, so we're going to call that line CC. Okay, so cross-sectional view of CC now. So if I were to sketch out a cross-sectional, so for example, if our structure looked like this, for example. Okay, so this is our cross-section view. Okay, for example, this is our cross-section view. Okay, so if we want to find Okay, we want to find the shear stress at point A. So shear stress at point A. Again, Eugene, don't call it point A. So shear stress at point D, shear stress at point E, and shear stress at point F. So what does this mean? Okay, so when we apply, right? When we apply, so we want to let me get this diagram below so when I write you can see better. Right? So what we see down here, right? So if you want to find, let's focus on the shear, okay? If we want to find the shear, right? The shear at point D, right? So this will be equal to V over I, right? Q at point D divided by T at point D. Okay, so this is how you find. And then if you want to look at the shear at point E, right? You still use the same V over I. What changes is the first moment of area of point E divided by the thickness at point what? E. Okay, and then again, we're going to look at the shear at point F. Right? So V over I is still the what? The same. The point of interest will change, but your first moment of area and the thickness will change. Are we clear? So you have to grasp this concept very clearly, or not it gets really confusing later on. Okay, it gets really confusing and later on. So regardless of the point of interest, so point D, E, and F are at different point of the cross section of our beam. The V over I are always a constant. You use the same V over I for point D, for point E, and for point F. What changes are your first moment of area at point D and the thickness at point D. The first moment of area at point E and the thickness at point E, and so on and so forth. So this you have to really grasp the concept really well. Again, if not, you can get really confused in this aspect. Okay.
So does that mean that you could essentially, theoretically, do it infinitely in any point on the beam?
Yep. Anyway.
So when we are designing something, or when we are analyzing a structure,
Wait,
how many?
can I hold you down there?
Yeah.
Your questions are very ahead, okay,
Oh, okay.
which is
Okay.
good. So I will go on first, then later on you'll clarify for you, okay? Because you are thinking ahead, the rest of student might not be thinking like, what are you asking about? You get
Okay.
coming from, okay? So
Okay. Yeah.
so your question is really valid, okay? But let's once I start teaching, it will answer everything.
Okay.
Okay.
Yeah.
Right. So now you have, so the next thing I want to clarify is what do I mean by first moment of area. Okay, so let's see what's first moment of area first. Then later on in our example, then I'll handle second moment of area. Okay, so let's deal with first moment of area. Okay, let's deal with first moment of area Q. So the formula for first moment of area is Q is equal to A y bar. Okay, so this is the formula for first moment of area, okay, which you all have to remember. Right, so A is known as the defined area. Okay, and this is in meter squared. And then Y bar is known as the distance of the centroid. Okay, distance of the centroid. with respect to the defined area. Okay, and this is in meters. Okay, so this is first moment of area. Okay, so let me see how are we going to apply this. Okay, so how are we going to apply this? So we're going to look into shearing stress in a thick wall section. Okay, we're going to look at shearing stress in a thick wall section. Hey. Okay, so I'm going to get a diagram over here. Okay, so you guys would have all these diagrams, okay, on Avenue to Learn. So we're going to look at this diagram first. Okay, so some of you might say, Eugene, how is this diagram related in a beam? So what we see, so again, we assume that we have a structure, right? Again, we assume that we have a structure. Right, simply supported. Okay, and then we have a certain load P, right? And then this is our transformation. X, Y, and we have rotation about our Z. So again, there's our point A, point B. Okay, it's okay. Point A, point B. And this is our section FF, for example. Okay, so what we are seeing now is our section FF. Okay, now we are seeing our section FF now. Okay, so this is what we see. So this happened to be a rectangular block. Okay, right. So if we were to draw our transformation, so you can see over here the transformation. So this is our Y, Z, and this is rotation about X. Okay, so now for this diagram, based on where the shear force will appear, so the shear force will come down in a VY direction. I'll use a different color. So this will come down, right? And this will come down in a VY direction, right? In a VY. So when it's in a VY direction, the area that we are going to consider, right, is going to be this area. Okay. So we are going to find the first moment of area. Okay, so the first moment of area okay, the first moment of area will be about the z-axis when the force is applied in VY direction. Okay, so what does this mean? This means this axis over here, right, is the axis that we are going to take the first moment of area, right? So for this case, we have QZ. So Q, first moment of area about the z-axis, right, is equal to the area, right? So it's about the z-axis. So the area is a y bar. So y bar, the distance, this is the what? Perpendicular distance, right? From the what? From the z-axis. Okay, right? So this QZ over here signify the first moment of area